Okay, so welcome to part 2 of the video on Minkowski's inequality. So I'm just going to have a little bit of a recap of what we did in the previous video. We want to prove, the thing we want to prove is that if we have x and y, two vectors in an LP space, i.e. x is equal to some sequence, x1, and I keep saying vectors, I'm so sorry, these are sequences, x1, x2, x3, etc. And we have y, which is equal to y1, y2, y3, etc. And you go on and on and on. So we have these two elements of this LP space. Then we want to prove that the summation I is equal to 1 to infinity of the modulus of xi plus yi to the power of p, and then raise that entire great number to the power of 1 over, not 1 over q, 1 over p, is less, that this value is less than or equal to the sum of the summation I is equal to 1 to infinity of the modulus of xi to the p to the power of 1 over p plus the summation I is equal to 1 to infinity the modulus of yi to the p over 1 over p. Now the first thing I want to discuss is that in the rest of the proof that we're going to show, we are going to assume that p is greater than 1, and the reason is we're going to want to apply Holder's inequality, and Holder's inequality needs that value, remember, p, to be greater than 1, and we're going to let this p, the p from this equation, be the p that's going to be in Holder's inequality as well. So firstly, let's just prove this statement simply if p is equal to 1, and then we'll prove it if p is greater than 1. So for p is equal to 1, then this statement becomes the summation I is equal to 1 to infinity, the modulus of xi plus yi to the power of 1, so I should put that 1, to the power of 1 divided by 1 is less than or equal to the summation I is equal to 1 to infinity, the modulus of xi to the 1 over to the power of 1 divided by 1 plus the summation I is equal to 1 to infinity of the modulus of yi to the p, to the 1 rather, over 1 over 1. So this basically just reduces down to the fact that the summation I is equal to 1 to infinity of the modulus of xi plus yi is less than or equal to the sum I is equal to 1 to infinity modulus of xi plus the modulus of yi. And that follows straight away from the fact that the modulus of xi plus the modulus of yi, for any two real numbers xi and yi, that it is true that this is less than or equal to the modulus of xi plus the modulus of yi. This is true for all I as an element of the natural numbers. Therefore, we can say that the summation from I is equal to 1 to n, or where n is some finite number of the modulus of xi plus yi, is less than or equal to the summation I is equal to 1 to n of the modulus of xi plus the modulus of yi. That's just because each term over here, in this over here, so x1 plus y1, the modulus of that will have a corresponding term over here. If you write out both additions, each one will have a corresponding term, and the bit that you're adding on this side will be greater than the bit that you're adding on this side. So overall, the summation here will be less than or equal to the summation over here. Okay, therefore, if we just take the limit as n approaches infinity of both of these sequences, the sum I is equal to 1 to infinity modulus of xi plus yi, sorry, that should be an n, the limit as n approaches infinity, is less than or equal to the limit as n approaches infinity of the modulus of I is equal to 1 to n, the modulus of xi plus what modulus of yi. Now, if x and y are both elements of L1, then that implies that the summation of the modulus of xi to the power of 1, I is equal to 1 to infinity, is less than plus infinity, and similarly it implies that the sum I is equal to 1 to infinity of yi is less than plus infinity. So this side is just the summation, is just the addition, is just add this one, whatever this is, which is a finite number, to this one over here. So you get that this, the limit of this sequence is less than or equal to some finite real number over here. Okay, and also this is a monotonically increasing sequence on this side because each of the terms of this series is positive. Therefore, if you take the summation up to n plus 1, that's going to be the summation up to n plus the modulus of xn plus 1 plus yn plus 1, so it's always going to be greater than the last term, and we know from real analysis that any monotonically increasing sequence like that does indeed have a limit, providing the sequence is bounded, which it is in this case because it's bounded by this number over here. Okay, so that's the proof that Minkowski's inequality does indeed hold true in the case that p is equal to 1. So, in the case that p is greater than 1, then we got to the stage of, this is true even if p is equal to 1, but we won't be able to use Holder's inequality from here. We've gotten to the stage where the sum from I is equal to 1 to n of the modulus of xi plus yi to the power of p is less than or equal to the summation I is equal to 1 to n of the modulus of xi times the modulus of xi plus yi to the power of p minus 1 plus the summation I is equal to 1 to n of the modulus of yi times the modulus of xi plus yi to the p minus 1. So we got to that. Now that does hold true for p is equal to 1, but the step that we apply next, where we're going to use Holder's inequality, will not work for p is equal to 1, which is why we've done p is equal to 1. We've proven Minkowski's inequality for p is equal to 1 in a separate case, basically. Okay, so now let me just remind you of what Holder's inequality said. The Holder's inequality for finite sums, as I showed you in the previous video, is the sum from I is equal to 1 to some n of ai bi is less than or equal to the summation j is equal to 1 to n of the modulus of ai to the p, to the u we said, but in fact we'll make it p now, we'll make it p over to the power of 1 over p. So I'm going to let this p over here, p is now greater than 1, so I'm going to let the p in this Holder's inequality be equal to the p over here, and we'll let the q be whatever you need to make q in order for this to hold. So k is equal to 1 to n of the modulus of bk, this should have been a j here, bk to the q to the power of 1 over q, and and the way q is defined is that it is the conjugate exponent of p, so 1 over p plus 1 over q is equal to 1. So, providing p is greater than 1, I can say that whatever these vectors ai, whatever these finite sequences ai and bi are, that this inequality holds, where the way I define q, where the way I get the number q is through, say, take the conjugate exponent of p. So now, what I'm going to do is I'm going to say that the sum from I is equal to 1 to n of the modulus of xi times xi plus yi to the power of p minus 1, the modulus of that, again because the modulus and multiplication interchange, I can do this quite happily. I can take the p minus 1 within the modulus sign because of the properties of the modulus sign, and I can combine the modulus of xi with this xi plus yi to the power of p minus 1. Okay, so I'm now viewing this as this bit in Holder's inequality. I'm going to view ai, I'm going to view the corresponding term of ai as xi, and I'm going to view bi's corresponding term as being this one here. So we now put it into this formula. It's going to be less than or equal to the summation from j is equal to 1 to n of the modulus of xj to the power of p, all to the power of 1 over p. And then on this bit I will get the summation k is equal to 1 to n. Now bk is just going to be the modulus of xk plus yk to the power of p minus 1, all of that in the modulus sign to the power of q, and then put big brackets around there, let me get this into your view, and then we want that all to the power of 1 over q, okay? So now I'll move this back over here. Right, we're running out of paper, fast. Do I have anything more to do to that? Yes, I do. Now, because this number xk plus y, Okay, we can now interchange the order of the modulus and the taking of the power to p minus 1. So basically I'm going to pull the power of p minus 1 outside of the modulus, so this will become less than or equal to, in fact I'll write the full thing out again, the sum from I is equal to 1 to n, let me just get it nicely on the right slant, of the modulus of xi times xi plus yi to the p minus 1, and then the modulus of that is less than or equal to, this remains exactly the same, j is equal to 1 to n xj to the p to the power of 1 over p, and then this other bit becomes the summation k is equal to 1 to n of the modulus of xk plus yk to the power of p minus 1 times q, and then all of that to the power of 1 over q. And it's time for another piece of paper. Okay, not on that there, so onwards then. Right, so let me just get this on the right angle. I want it to be as perfect as possible. Okay, so p minus 1 times q. This is equal to pq minus q. Now, if you remember from the conjugate exponent formula here, then we can multiply up by p. We can multiply both sides by p and q, so we'll get q plus p is equal to pq. So if we take the q onto the other side, we get that p is equal to pq minus q. So we can replace pq minus q, or p minus 1 times q, by p. So p minus 1 times q is just going to be equal to p. So this becomes, over here, this bit here becomes the summation k is equal to 1 to n of the modulus of xk plus yk to the power of p, and then all of that to the power of 1 over q. Right, so that's great. Okay, so now what we're going to do is, if we go back up to this bit up here, we've done this one here, now we're going to apply Holder's inequality to this bit here. So if we apply Holder's inequality to that bit, we have, we start off with the sum, I is equal to 1 to n of the modulus of yi times xi plus yi to the power of p minus 1. Okay, so if I bring it back down to show you, so all I've done is pulled the p minus 1 within the complex modulus sign, and then I've combined these two together to get them both within the same modulus sign. So that indeed is equal to that, okay? And now I'm going to apply Holder's inequality to it. So Holder's inequality is, where is Holder's inequality? Holder's inequality is there. I'm going to view again yi, I'm going to view as being the ai, and I'm going to view this big monster here as being bi. Okay, so this is less than or equal to the summation j is equal to 1 to n of the modulus of aj, which is equal to the modulus of yj to the power of p, all to the power of 1 divided by p, times the summation k is equal to 1 to n of bk, which is again equal to the xi plus yi, oh sorry, xk it should be, plus yk to the power of p minus 1, all of that in a modulus, and I'm going to pull it out so you can see it properly, to the power of q, all of that to the power of 1 over q. And again, I can apply the same trick here. I can say pull this p minus 1 out and have it multiplied with the q, and then that will just equal p, because p minus 1 times q is equal to pq minus q, which we've shown is equal to p by the fact that that p and q are conjugate exponents. Okay, so this becomes equal to the summation k is equal to 1 to n of the modulus of xk plus yk to the p, and then we've got all of that to the power of 1 over q. Okay, so now what we do is we go back to this inequality up here. So we have that this thing here is less than or equal, and in fact I'm going to rewrite it back down at the bottom here. We get that the summation from I is equal to 1 to n, this was the original problem that we had, from we found that the summation from I is equal to 1 to n of the modulus of xi plus yi to the power of p was less than or equal to the summation I is equal to 1 to n of the modulus of xi times the modulus of xi plus yi to the power of p minus 1, plus the summation I is equal to 1 to n of the modulus of yi times the modulus of xi plus yi to the power of p minus 1. Now, through Holder's inequality, if I just sort of, summarize everything that we've done so far, from Holder's inequality, we got that the sum as I is equal to 1 to n of the modulus of xi times the modulus of xi plus yi to the p minus 1, we got that this was less than or equal to the summation j is equal to 1 to n of xj to the power of p, all of that to the power of 1 over p, times the summation k is equal to 1 to n of the modulus of xk plus yk to the power of p, all of that to the power of 1 over q, and we got that the summation I is equal to 1 to n the modulus of yi times the modulus of xi plus yi to the power of p minus 1, that was less than or equal to the summation j is equal to 1 to n of the modulus of yj to the power of p, all of that to the power of 1 over p, times the summation k is equal to 1 to n of the modulus of xk plus yk to the power of p, all of that summation summed up to n, all of that to the power of 1 over q. Okay, so that's where we are at the moment. We have all of this, so we're going to combine these two together. So I can add these two together and add these two together, and basically I get that if I add those two, that is less than or equal to the sum of these two. Okay, so therefore by the transitive property, if this is less than or equal to this, and this is less than or equal to this, then this is less than or equal to this. So we get that the sum I is equal to 1 to n of the modulus of xi plus yi to the power of p is less than or equal to. Now you'll notice there is some common factor here. This term here is common between these two, so we'll factorize that out and put it at the front. The sum from k is equal to 1 to n of the modulus of xk plus yk, and I'll move this up, okay, yk to the power of p, all of that to the power of 1 over q, and then in great big brackets, and I'll make them square, we have the summation from j is equal to 1 to n of the modulus of xj to the power of p, all of that to the power of 1 over p, and then I'll put down here plus the summation j is equal to 1 to n of the modulus of yj to the power of p, all of that to the power of 1 over p, and then close those big square brackets. Okay, so this is looking very hopeful because here we have the exact term that we wanted in Minkowski's inequality. So what we're now going to do is we're going to divide through by this on both sides. So this is a positive real number. Well, it's a non-negative real number. So we can say, and it's... oh, well, we do need the fact that it isn't equal to 0. We do need the fact that this isn't equal to 0, the reason being that we need to be able to have its multiplicative inverse. So if it's a positive real number, i.e. it's not 0, then we can divide, well, we can say it has a multiplicative inverse, which is also a non-negative real number, and we can multiply both sides by the multiplicative inverse of this. So we can divide, effectively, by it. So we get that the summation I is equal to 1 to n of the modulus of xi plus yi to the power of p divided by the summation k is equal to 1 to n of the modulus of xk plus yk, all of that to the power of 1 over q, is less than or equal to this great big thing in the brackets here. So j is equal to 1 to, is it still in view? Yep, j is equal to 1 to n, the modulus of xj to the power of p to the power of 1 over p, plus the summation j is equal to 1 to n of yj, the modulus of yj to the power of p, all of that to the power of 1 over p. Okay, and remember, I just want to recall that getting these inequalities here required p to be greater than 1. So that's why we can't use this proof to prove that it was that the Minkowski inequality worked for p is equal to 1. So that's why we needed to prove that separately. Okay, so now let's just get the Minkowski inequality from this. You will notice that this number is the same as this number. So this effectively is this number to the power of 1, so we can view this as if you had a to the power of k divided by a to the power of l, then we know that by basic laws of exponentials it is a to the k minus l. So this side is effectively equal to the summation I is equal to 1 to n of the modulus of xi plus yi to the power of p to the power of 1 minus 1 over q. But that's great because 1 minus 1 over q is equal to 1 over p, because 1 over p plus 1 over q is equal to 1, because they were conjugate exponents. So this just becomes the summation I is equal to 1 to n of the modulus of xi plus yi to the power of p, all to the power of 1 over p. So now what we have is the finite Minkowski inequality. We have that the summation I is equal to 1 to n of the modulus of xi plus yi to the power of p, all to the power of 1 over p, is less than or equal to this one. Well, the summation j is equal to 1 to n of the modulus of xj to the power of p, all to the power of 1 over p, plus the summation j is equal to 1 to n of the modulus of yj to the power of p, all to the power of 1 over p. So that is what we're going to use to prove that those triangle inequalities that we had on Euclidean and unitary spaces. So to prove that Euclidean and unitary spaces are metric spaces, we need to prove the final axiom, the triangle inequality, and this is how we're going to do it. We're going to use this inequality here, the finite Minkowski inequality. Okay, so now what we're going to do is just so that we can, because we set out trying to prove it for LP spaces, and Minkowski's inequality actually works for the infinite ones. So we've got at the moment we've got the finite Minkowski inequality, which is I is equal to 1 to n the modulus of xi plus yi to the power of p to the power of 1 over p is less than or equal to the summation I is equal to 1 to n the modulus of xi to the power of p to the power of 1 over p, plus the summation I is equal to 1 to n let me bring this down a bit, the modulus of yi to the power of p to the power of 1 over p. Okay, so that's what we've got so far. Now basically we just take, this is true for all n is an element of the natural numbers, so we just take the limit as n approaches infinity. So if we take the limit, that's right, limit as n approaches infinity, it's less than or equal to the limit as this side approaches infinity. But we know what the limit of these are as they, well, we don't know what they are, but we know that since x and y are elements of the LP space, we know that the summation I is equal to 1 to infinity of the modulus of xi to the power of p is equal to some finite value, and therefore that to the power of 1 over p is also equal to some finite value. So we know that this side converges to some finite value, okay? And on this side what we get is that this is a monotonically increasing sequence. As you make n bigger, then the thing inside the power, this summation here, is going to get bigger. It's monotonically increasing. And when you take 1 over p power of something that is getting bigger, the 1 over p power of that will also get bigger. So this is monotonically increasing. So all we need to prove is that it's bounded. Oh look, we have proven it's bounded, so its limit does exist. And its limit is finite, which proves the original question of whether x plus y is indeed an element of LP. We have proven that yes, this summation I is equal to 1 to infinity must be finite. So we therefore get, by taking the limit as n approaches infinity, we get the Minkowski's inequality, which is that the summation I is equal to 1 to infinity the modulus of xi plus yi to the power of p to the power of 1 over p is less than or equal to the summation I is equal to 1 to infinity the modulus of xi to the p to the power of 1 over p plus the summation I is equal to 1 to infinity the modulus of yi to the power of p to the power of 1 over p. And that's everything that we're going to do in this video.